Oh, yang masih itu diskusinya paling fix, biar balik lagi itu kan.
Tadi kayaknya
Ya, Mas Jawar kelempar.
saya kira ini ya.
Tapi sekarang udah.
Apa?
Apa? Itu berada di suara kamu bilang kamu kelempar. Dari 2 minutes.
Yeah, well, we look at us like at some point
Di ini harus dimatiin aja.
but don't worry. Yeah, so we are very flexible. Oh, are we not? Oh, I need to share screen.
Iya, so.
Share screen in the Zoom.
Ya,
So, I think if I it should share that in the bottom. I think if I do that,
Oke.
share. Yeah, just
Sebenarnya ada
Is
lama.
that
Oh,
is that
enggak.
not?
No.
Is it okay? Yes, no?
Hah?
Is it okay or not?
Yes, this is okay.
In the Zoom, it's good.
In Zoom is clear.
Okay.
So maybe you need to check the.
Oh, yeah. That's okay, because I can click here and just see.
Yeah.
Okay. I don't think it's the same.
Jadi, oke. Ini. Oh.
Okay. What is it?
So what is again?
In the share screen?
Yes,
Okay,
share screen.
so good.
So
That was. I like the way it works. Okay, perfect. We need to put the custom on here. Got it. See this custom. Yeah, I see.
so hang on. Di Zoom.
Okay, wait back.
Belum di set.
Okay, perfect.
Oh,
I'm not sure you can see it. I just want to make sure I stay on time. This is not Japan. Okay, yeah. Oh, yeah.
So, okay. Good morning, everyone. Selamat pagi. Assalamualaikum warahmatullahi wabarakatuh. So, yeah, it's very good occasion that today we have a special guest from the US, and I would like to introduce him in this very good time. And yeah, he's Dr. Eric Rosenthal. He is my former colleague when I was PhD student in Tokyo University about 11 years ago, 2012 or I forgot actually. But yeah, we had one publication together, and you can check physical review. The title is Exciton Coherence Phonon something. I already forgot the answer. But yeah, Eric graduated from University of Pennsylvania for undergrad, and then he continued to PhD course in University of Colorado, and then he is now a postdoctoral scholar at Stanford University, more specifically Poppy Group. Is it correct? Yeah. And yes, he's actually on vacation, but we catch him to come here for to give us some presentations about the tin-vacancy qubit in diamond, and this is believed to be an emerging platform for quantum networks. So yeah, Eric will give presentation for 1 hour, and then there will be 30 minutes for discussion. But feel free to interrupt. Is it okay? To interrupt if you of your presentation. Yeah, feel free to interrupt if you have some unclear statements or unclear explanations. Feel free to interrupt, but try to attend, okay? Then do not suddenly cut the presentation. Okay, so are you ready? No problem. Okay, so yes, please start. Time is yours.
Well, thank you for the kind introduction, Nugraha. It's wonderful to be here in Indonesia. Thank you everybody for coming. This is my first time in Indonesia. Actually, I arrived yesterday afternoon, so I'm just. Oh, thank you. Can everyone hear me? Yes. Perfect. Yeah. But it's really wonderful to be here and to chat about science and visit. And, thank you all for listening. Like Nugraha said, please feel free to interrupt me at any time if you have any questions. And I'll say Nugraha was actually sort of my first grad student mentor actually that summer at undergrad a really long time ago. So as I look back on that summer really fondly, and it's really wonderful to connect again like a decade later. With that, thanks again, and I'll tell you about our work on the tin-vacancy qubit and diamond. I'm Eric Rosenthal. I'm a postdoc from the Vukovic group at Stanford. And most of the work I'll tell you about is in our publication from last year. And then also this is the you need to move the poster. Oh yeah. Oh, move the cursor here. But sorry, I'm just debugging the
Yes.
I can just use this.
Thanks.
Now I'm slightly confused. That's okay. I'll do it. Yeah, but I also want to advertise our recent work. Yes, just on the archive yesterday. Actually, it was fun. Preparing for this trip, we also submitted the paper earlier this week, so you can read about everything we talk about. Yeah. In these two references here, and the main thing I'll tell you about is really how we can control these color centers in diamond as spin qubits. So in all our experiments, we have this sort of artificial atomic system that's a defect center trapped in a diamond lattice, and it has some spin. It's really just a single electron spin sitting in this chip of diamond. And the sort of punchline is we can control the state of the spin, whether it's down or up, and we can also measure the state of the spin. And so there's some motivation about why people want to do this, but then really most of the talk is the technical way in which we can do this control and readout. To spoil the punchline. But first, I want to thank all of our many wonderful collaborators. So I want to thank folks in the Vukovic group, graduate students. There's Hope, Jakob. I think some of you actually know, maybe I don't know Jakob. But I work with him. He's also went to Japan last summer. Hannah and Abby, Shobik, Gio, Chris are postdocs. And then Junhee Choi, another faculty at Stanford, is our collaborator. And folks at Argonne and Sandia National Labs help us with the sample growth and materials preparation. And I want to especially thank Chris for his mentorship on the sort of spin control part of this talk, the first half of the talk. And then thank Shobik for help on and collaboration on the readout part of this talk. So it's great to work with such excellent people, and I want to especially thank Jelena, our supervisor. So to launch into things, I think there's lots of different types of qubits and quantum technology and reasons why we might be excited about quantum. But specifically for defect centers in diamond, I want to sort of focus on this quantum network application. Thank you. Oh, it's perfect. Thank you. I really want to focus on why you might want to sort of these color centers in diamond are a way to entangle qubits in very spatially separated locations. So you can envision I have a spin in San Francisco and you have a spin here in Indonesia, and we can somehow prepare the Bell state where those two spins are really entangled together, despite being physically in very, very separate locations. And that's something that, to sort of the best of our knowledge, you want to mediate with light. Light is this, it's this very high energy thing. So you can send sort of a photon down an optical fiber, and at some wavelengths, it's not very lossy. There's not a lot of decoherence because it's this really high energy photon. High energy compared to like a microwave single photon or something. But sort of in some world where you want to make this quantum network and mediate interactions with light, color centers in solid state systems are sort of understood as a good way of doing this because they have long-lived spin degrees of freedom, and you can entangle that spin with an optical photon. So there's it sort of has all of the elements you need, and it's just a question of actually doing this. And the sort of traditional focus of the Vukovic group is really the group I'm in now is the nanophotonic side of this. So you have these spin qubits in solid state, and you want to get the light out, and you can imagine doing that with some photonic structure. So your atomic system in your solid state just wants to emit light everywhere. But if it can emit light preferentially just into a waveguide or a cavity, you can imagine collecting that light very efficiently and then actually realizing some sort of network like this. And so that's what we're looking at here is a grating coupler in diamond. Diamond sort of it's a good material for hosting solid state spin defects, but it's a tricky material to do photonics with. So that's sort of historically a lot of the work in our group. But then what I'll tell you about today is sort of more adding degrees of complexity to the experiment, including controlling the spins. We'd like to incorporate this with photonics and kind of bring it all together in the future. But what I'll tell you about today is really on the sort of quantum control, quantum measurement of solid state spin side of things. And so, this is kind of what we want to build. What do we actually have now? The state of the art in this field is a 3-node quantum network by Ronald Hansen's group at Delft. So in this paper, I think the 3-node one is the 2021 paper. They have nitrogen vacancy centers in diamond. So a different type of spin qubit than what I'll tell you about today, but a sort of an older, more well understood one. They have 3 of them in separate cryostats. One of which is in a separate building, like some distance away down the hall. And they can really entangle the spins in these 3 separate cryostats using light. And how exactly that works is always kind of a little bit confusing to me. I've never done that experiment, but it sort of involves taking the light emitted from these different spin systems and interfering it on some deep splitter to erase the witch path information. So if I just have two nodes, and I do like a perfect spin photon gate in each node, and then I'm emitting identical photons from each node, and I interfere them on a beam splitter, and then something about if I get a click or not allows me to prepare a entangled state between the spins. And I think for sort of more information on that, I think these references are really good. But I want to just kind of say we want to build some sort of at scale worldwide quantum network of entangled spins. And the state of the art today is really only 3 in sort of one small location. And so we have a lot of work to do, and we need to solve a lot of technical problems if we're actually going to do this. And a lot of the problems are, there's a lot of really excellent work you can do with nitrogen vacancy centers in diamond, but there are just some physical limitations of that qubit that sort of makes these experiments hard and sort of reduces the way you're able to do this. And so the field is kind of moving to different types of qubits, and folks are catching up. Just in the last year, there's been nice 2-node networks from using silicon vacancy centers in diamond and from Harvard, and rare earth ions very recently from Caltech. And so, the field is progressing, and controlling one spin qubit is it's sort of hard for us. That's kind of like a PhD postdoc scale project. Doing 2 nodes together is very hard because then you have to worry about the synchronization of your 2 setups, and there's a lot more going on. Doing 100, nobody knows how to do that today right now. So that's kind of where the field is going now. And so, I said the qubits themselves were maybe some of the problem. We need better qubits. We need, and what exactly do I mean by that? Well, at a bird's eye level, these solid state atomic defects are
living in the band gap of some crystal. And that's good and bad. So your defect center is trapped in your crystal, which means you don't have to make some magneto-optical trap or anything like that. Like the atom is just always there. You don't have to do any extra work to keep it there. But it's bad because there's a lot of other stuff going on in your crystal that can mess up your qubit property. So within the band gap of your material, there's some defect system that has an energy transition. That's for the ones we work at, they're in the visible light. So kind of like red light sitting in the diamond band gap. And this is sort of a relatively noiseless, nice environment for this defect. And then a lot of these, like the NV, the SnV, which I'll tell you about, a lot of these defects have a spin degree of freedom as well. So this is really some property of an electron that's up or down that we're going to use as our qubit. And I said the NV a few times now. They've kind of been around for 20 years. You can do the readout just with a green laser, sort of like the easiest type of laser you can buy. And it works well even at room temperature, so you don't need a cryostat. So these are really good for biosensing. They're also what folks that make quantum networks out of. And this center is formed by a nitrogen, or sort of two carbons missing in your diamond lattice, one replaced by a nitrogen, another replaced by nothing. And this is kind of like the standard qubit in the field that all the other qubits are compared to. And then a big problem with all of these qubits, but especially the NV, is noise. So here's just some raw data from our lab, not actually on the NV, but just to illustrate. And so we're sort of measuring this optical transition as the color axis here, and we're, so this is like detuning from some particular wavelength red, and we're taking many scans. Like each scan takes like 10 seconds or something, and we're scanning, and we see this nice stable optical line, and it's actually not totally stable. You can see it wandering around a little bit, but this is good. This is like what we want it to look like. For lots of reasons, it can actually look like this, right? So it's always bouncing around, and this isn't an SnV qubit. It's sort of supposed to be stable, but if you are trying to do these quantum experiments with the NV, it kind of looks like this a lot. And that makes it really hard to like have two of them that are emitting exactly the same type of photons in a very sort of controlled way, right? Like if you have two things always jittering, you're sort of waiting for them to like stop jittering and look kind of the same. And maybe for two you can do that, but for 100, I think it's not really possible, right? And so if you have your nice like Rydberg atom in your magneto-optical trap, right? Every atom is exactly the same. And with color centers, they're both different, and they're like different in like a wandering manner, right? And so that's kind of what a main problem with the field, I think. And so there's a lot of different ways people are trying to get around this problem. So you can imagine just what's causing it to jitter, right? It's like this optical transition is sensitive to some electronic noise in the environment. So with the NV, it's a first order effect. So its transition is first order sensitive to a charge around it. And a lot of those charges are coming from surfaces, which is why it's hard to integrate these defects into the nanophotonic structures we need, or we think we need. And so you can imagine just trying to avoid that noise by making sure your surfaces are really clean, like passivating them. So putting some sort of atomic layer like on top of your surface that's controlled, and everywhere on this surface looks exactly the same. So that's sort of a promising avenue. You can also do something active to cancel noise. So here is my colleague Chris Anderson in silicon carbide defects is actually putting the defect in a PIN diode, so he can sort of bias this diode and change the charge environment. And sort of when it's biased correctly here on the right, it's like more stable. It's a narrower line. So you can do that. It doesn't work for all defects. It doesn't work for the ones in diamond. Or you can just use a defect that's less sensitive to noise in its environment. And that's what we're going to do today with these tin-vacancy centers in diamond, which are a class of group 4 centers. And one of the nice features about them is that they have no first order sensitivity to stray electric fields. So their optical line, if there's some fluctuating charge, it's not sensitive to that. It's still second order sensitive, so it moves a little bit, but it's not first order sensitive, and that makes it very stable. And that's sort of why on a good day we can get something that looks like this. relatively easily. I'm not sure what was going on this day, but that's why we like group fours. They're not the only defect that has this problem. Yeah.
What is BRIN?
Oh, sorry. Yeah, that's for electro-optic modulator. But that's basically we're doing this scanning with we have a laser and then we're modulating it. So we're making sort of sidebands on that laser and we're changing the frequency of the modulation. So we're scanning the sidebands repeatedly because it's easier to do that than actually change the laser frequency. Like we can scan it much faster.
The y-axis.
Yep, the y-axis is just a repeated number of scans. So we're doing like, scan number 1, scan number 2, scan number 3, and each scan is sort of like quarter seconds in this case. But you can do it with any scan speed you like. Yep, sorry, great question. Yep. So for this talk, we'll focus on group fours, which have this inherent insensitivity to noise, which lets us build sort of relatively stable systems with them most of the time. Yes, and the sort of level structure of a group 4 center in diamond, at zero magnetic field, it has these 2 ground states, and it has these 2 excited states. For tin, the one we work on, so in our work, this X atom is a tin vacancy, so there's 2 carbons missing and a tin in between them. It has this nice symmetric structure. It's sort of why it has this insensitivity compared to the NV, which is not symmetric. So we have this tin replacing the X, and then there's 4 different ways you might do this. So there's silicon vacancy centers in diamond, germanium, tin, and lead. And these are different group 4 centers in diamond. They all emit at slightly different wavelengths, all within visible light. And the salient difference between all of them is the strength of this ground state splitting. So for silicon vacancy center and diamond, what they do at Harvard and AWS and 2-node networks now, this is 50 gigahertz. With germanium, it's 130. With tin, it's 800. It keeps going up. And you want this difference to be really big because there's some energy, h bar omega, associated with that. That's compared to thermal energy from KBT. And you basically want to operate in some limit where this second level here is thermally not populated ever. So for a silicon vacancy center in diamond at 50 gigahertz, you have to operate at about 100 millikelvin in a dilution fridge. It's very sensitive to heating and sensitive to temperature. For tin, because this splitting is a lot bigger because it's 800 gigahertz, we can do all our experiments at a couple of Kelvin. So we still need a cryostat, but it's a lot more economical because we can just use a helium-4 cryostat. We have sort of a vat of helium-4 we're just pumping on. And that's sort of a simpler, more scalable process.
I'm just wondering, so this is from theory?
Oh, yes, sorry, this is from theory. Yeah, these are all theory, yeah. For silicon and now from our work with tin and others, people have actually measured 2 of these curves. But sort of, yeah, definitely these are the theory plots. Yeah. For what the spin lifetime or the T1 time is expected to be as a function of temperature. Yeah. And so you basically, sorry, I didn't say, but the sort of temperature threshold where you could have like a second long energy relaxation time for your spin is kind of like a couple Kelvin for tin and a couple hundred millikelvin for silicon vacancies. So that's basically I was trying to motivate for you why we like group 4s because they're insensitive to noise. And now I'm trying to motivate for you why we like tin compared to other group 4 centers like silicon vacancy center. So within the scoopable color centers we're doing group 4s, and within group 4s we're doing tin. That's kind of the message. Lead is quite interesting too. There's less work on it. I think it emits at sort of a slightly annoying wavelength. I mean, so does tin. Some of the sort of historical reason why the field has started with the silicon vacancy center, I think, is because it emits at a much more economically accessible wavelength for lasers, and it's also a smaller atom, so it's kind of you might imagine there's sort of like something worse is going on if you're implanting this really, really heavy atom into carbon, or into diamond, which is this really light carbon atom. So there's some like, you know, what temperature you need to anneal your diamond when you implant it and stuff like that. That's kind of worked out to do all these experiments.
So with the heavier the atom, the gap is growing in front.
Exactly. Yeah, that's the overall message. Exactly, is that as you go down this periodic table for these defects in diamond, the gap grows and grows, and we're operating sort of like you know, pretty far down. Yeah.
So it's easier to couple the optical system with light than because the frequency is close to the.
Yeah, so for the optical systems, we're always coupling between this lowest state in the ground state and this lowest state in the sort of excited of the two levels. Yeah, sorry. But we really we want this second level here not to be thermally populated. Yeah, exactly. That's because any sort of thermal population in that is going to limit our abilities.
So this is why do you use group 4? Because usually N-vacancy and hydrogen vacancy has like unpaired electron, but group 4 has no unpaired electron.
I think the question is how we get possible to make this one.
Yeah. I think that's a really good question. I think it's something about like you have 2 carbons missing. I think it's like if you had some like group 4 defects where the group 4 was just replacing a carbon, I'm not sure you would have any unpaired electron. But it's a good question. I don't really know the answer to. I can tell you it's spin 1/2, so I can tell you when I turn on a magnetic field, all these levels split into 2. But yeah, more than that, I deeply don't quite understand why.
But it's possible to make it.
Yeah. Cool. So maybe, yeah, if there's any more questions on sort of the motivation, now's maybe a good time, and then I'll tell you more about how we can understand the specifics of the tin-vacancy center, and then I'll tell you about spin control and then about readout.
Maybe back to general question.
Yeah.
So as we know that the relevant have a large bandgap introduction.
Yes.
So that means you are introduce the defect on the bandgap to make localized spectrum.
Yeah, I think that's exactly right. Yeah, so in practice we try to buy a sort of electronic grade diamond, which is lacking in other impurities. It's just very pure diamond, and then we implant some blanket implants of like a relatively low amount of atoms per unit square into the chip.
Yes.
At some depth of maybe 100 nanometers or so, which is set by sort of how hard you implant them. And then we anneal the chip, and that kind of just, many of those tin atoms just kind of like form to be these defects that have this energy structured in the magnet. So there's not a ton we can do as experimentalists other than that, but it just sort of works like some high enough fraction of its time. Yeah.
One quick question.
Yeah.
In anti-sensing, get very careful with lasers. Because if you put a lot of power to them, that the NP minus would migrate into NP.
Yep.
And stuff. How about this?
Exactly the same problem. Yeah. So you got to be careful. In fact, on sort of a bad day in lab, when like sometimes it's blinking off. Like here, it seems like it's kind of jittering between different places, but sometimes you'll see it just blink off, and that's because it probably goes into some other charge state. So there's other, we like the negatively charged silicon or tin vacancies that are in diamond, but there's other charge states that the same atom is kind of blinking on and off in between, and those others aren't particularly active, and so that's a big problem. It's very dependent on like the sort of power and wavelength of the lasers you use to control it, and I think for each defect it's a little bit different. So
But it's the same problem.
Yeah, exactly the same problem. Yeah, exactly the same problem. Yeah, so and I think it's something about it being really in solid state. There's so many things it can do. It's a very messy system. Great. So now I'll tell you about sort of specifically how the SnV-center works and how our experiments work a little bit. So we have, as I was saying, we implant tin into these diamond chips. We can do that commercially or just in a blanket implant, or we can do it in a focused way with so-called focused ion beam. But it's always this probabilistic process. We can't deterministically implant single atoms in single spaces yet. Maybe one day people can. For now, we can't. And so we have these pillar structures we etch into the chip. And then we can focally shine a laser onto these structures. So here's a photograph of our experimental setup. So this is the sample stick of a chromostat. The chromostat has a vector magnet in it, so we can apply a magnetic field. And then we have some microwave control. So we actually have a wire bond draped over the chip here. It's sort of the simpler thing we can do than actually fabricating some metal structure on the chip, although there's sort of pros and cons of doing that versus this wire bond which is draped over the chip. But we can have this microwave control, so we can apply an AC magnetic field at the emitter location as well as this background DC magnetic field for our vector magnet. And then here's an objective. So this is like a lens that's focusing light onto some spot on the chip. And we can shine the light in and out. And unfortunately for these effects, we can work in visible light. So we can see, we have a red laser. You can actually just, I never looked into the beam, but you can see by eye that it's red. And we also have a green laser, see by eye and screen. So it's sort of like more beginner friendly optics than some of these invisible lasers that are a little more dangerous. But the light's coming in and out. And then if you were to look at the chip, so here's an optical image, and we have all these photonic pillars in them. So we implant our tin onto our chip, and then we etch away most of the surface. And so we have these pillars, and we also have mesas in between them. I'm not sure. This was just some old design they decided on like 5 years ago before my time in this group. But it's a good design. And you have these arrays, and it's nice because they're sort of photonic structures. So these like pillars are really designed to scatter light preferentially upwards into your collection rather than every which way if it was just in bulk. And in practice, it also makes it easy to kind of scan around and find a pillar you like. So we have these arrays of sort of 10 by 10, and they're all labeled like row 1, row 2, row 3. So you can sort of deterministically go back to a pillar you like, which is very hard to do in a bulk where everything kind of looks the same. And then for this talk, all the data I'll be telling you about, we actually think our sort of favorite and SNV we like is actually in one of these mesas. Just so by very finely scanning around, the light is sort of maximized when our like collection focus is on one of these mesa structures, which is not actually optimal. It's where we think it is. Let's see, what else about the chip? Yeah, we can scan around, but this chip is sitting on some piezoelectric positioners. So we have you can scan around either by changing the focus of your laser across the chip, or by scanning keeping your laser focused at a spot and scanning your chip around. And then you can do sort of this field. But yeah, we have chips like this, and I think the dream is really to do these same sorts of experiments in a photonic structure like the one in my intro slide, where you're controlling the light a little bit better than just with the pillar, but that's okay for me. It's still a lot of sense. Any questions on the chip?
Is pillar made out of diamond?
Yep, that's right. Yeah, so we can etch into the diamond with a dry etch just to remove the top sort of micron and selectively.
Why you need this kind of structure? I mean,
Oh yeah, great question. Yeah, so if your emitter is just in bulk, it's emitting light sort of more or less kind of like uniformly everywhere. But then the diamond is this high index material, so the speed of light is slower in your diamond. And it's not quite total internal reflection, but most of the light it emits will be scattered sort of preferentially down into your diamond because it's this high index material, and then the vacuum above it is this low index material. And so that makes it in practice really hard to measure because all your measurements are collecting light at this bit. Instead, if you have a subphotonic structure that can preferentially change how the light is scattered into your measurement.
Please explain again how to estimate the position of the frequency in the system.
Yeah, so we have a fine piezoelectric positioner. So we focus our laser maybe I can just show a backup slide here now. It's taking let me not try to do this now. But there's like a very, you can sort of see on like a camera that you're focused right onto a particular spot on your diamond chip, like say onto a pillar. And then you can do this like fine scanning around the pillar, and you'll see, and you're measuring how much signal you get of emitted light as a function of like where exactly you're scanning. And we can see it's maximized on the mesa. And the focal spot of our beam is like about 500 nanometers or so. And all the features in our mesas are kind of like 5 microns between like on this mesa structure. So we have sort of relatively fine control compared to the dimensions of our structures. But we don't know for sure.
So the frequency will emit light?
Yes, that's right. Yeah, it emits light when we shine our laser on it. Yeah, my PowerPoint is being a little glitchy for me right now. Let me try using some other apps. Okay, maybe that's better. Pardon the technical difficulties. Yeah. Oh, right. Perfect. Thank you. Sorry about that. Perfect. Okay. Yep. So let me tell you how we measure these qubits. So we have we have this level structure with the 4 different levels, and we're going to shine light onto it. And then it has this amazing property where if we shine a green laser at 532 nanometers, and we collect the emitted light, and then we filter it out on a spectrometer to look at the wavelength, we see these 2 peaks around 619 and 620 nanometers. And so we see these 2 transitions, and one we're going to call it the C transition is between these levels, and the other between these 2 levels. And so when we see this nice 2-peak structure with this splitting of about 900 gigahertz, that tells us we have a tin-vacancy center. We're very happy, and we know sort of from the peak of this measurement like exactly what wavelength this is emitting. And so different centers, they'll all have these peaks at slightly different wavelengths and sometimes different splittings as well, depending on how strained the diamond lattice is rapid. So this is kind of the characteristic signal we see sort of at the beginning of our experiments.
So this matches with the previous model.
Exactly. That's exactly right. Yeah, and it's a little bit different. It's not. Yeah, and there's a reason it's different. I'll tell you in a second. But it's sort of more or less about what you expect. And then if you were to zoom out, so in wavelength here we're just looking at a couple of nanometers, but here we're looking at like 100 nanometers. You actually see this sort of stronger emission at slightly lower or slightly higher wavelengths than this peak. And this is what we call the phonon sideband. So in the literature, these coherent optical transitions are called the 0 phonon lines. And this is called the phonon sideband, where any photon emitting in this sideband is, there's also a phonon being emitted in the lattice for sort of energy conservation reason. Like if you're excited and then it decays to the ground state, it's not emitting one photon at the transition frequency, it's emitting some lower energy photon and also photons. And in practice, this lets us sort of measure our qubit by shining a red laser, but then in our collection path, filtering out the red laser and collecting only the photon sideband. So all of the data I'm going to show you in the rest of the talk, we are just, we have some filters before our collector that are just sort of encapsulating this problem. Yeah.
That phonon sideband is also called phonon ring.
I think so.
Because like, yeah, I read some paper discuss about phonon ring with the same definition as you.
Got it. I hadn't seen phonon ring before, but I'd be almost positive it's the same thing. Yeah. Great. So we have this energy level structure. We know how to measure our qubit now, and now we're going to turn on a magnetic field. And so for all group 4 centers in Diamond, these levels will split into 2 different spin levels when you turn on the magnetic field. So you have this spin down state, which I'll call 1, spin up state, which we'll call 2, and this is what we want to. These lowest 2 is what we want to control as our qubit. And also the splitting between the levels in the upper state is a little bit different from the splitting in the levels in the lower state, and that leads to these different spectrally distinguishable transitions. So now instead of just having a C transition between here and here, we have actually these 4 different transitions we can address between all of these different spin states. And then so here in this plot, we're shining a green laser and measure it. Now we're going to actually, for the rest of the talk, we're going to shine a red laser to resonantly excite these transitions. So like the A1 transition, it's about like 619 nanometers, whatever. We're going to tune our laser near there, and then we're going to change the wavelength of that laser slightly and scan it through these transitions. And when we do that, we for technical reasons, we add a little bit of green as well. But we see these peaks in emission into the photon sideband when our laser is resonant with the transitions. And that's the color axis on this plot. And we see these 2 lines that are sort of pretty stable, but wandering around a little bit here. This was a good day in lab, so it was stable for like 6 hours. And all of our measurements basically are going to be driving on these transitions. So yeah, of course. Yes. So I think it's like, so for the magnetic field I'm using, this spacing is relatively small, but it's sort of, I know which, I'm basically parking my laser at 1 wavelength, and I'm modulating it to make a sideband on that laser, and I'm sweeping the sideband like continuously on this y-axis, and then I see sort of a first peak and then a second peak, and so I can sort of know which of these transitions is lower energy and then higher energy, and then from the magnetic field I'm operating at, I sort of know the A1 transition is supposed to be like lower than the B2 transition. And then I can infer it. But it's pretty easy to mix up. So and it ends up basically not that. Yes, I do actually. I'll show you in a second. But it's very dependent on both the amplitude and the angle of the magnetic field. Yeah. So basically, I said we have a vector magnet too. We only actually have 2 foils on our vector magnet, not 3. So the spin is pointing at some direction in the diamond lattice set by the sort of crystallographic orientation of the carbons in your diamond. And so the spin is pointing at like, 55 degrees that way or something. And you're sweeping this magnet in a big circle that's not totally aligned with where your spin is. But you're doing that sweep. So this angle called zeta is the angle we're sweeping. And then this bottom plot is what I just showed you, where we are doing this measurement where we're sweeping the laser through these transition frequencies. And then the top plot is the difference between like the 1 and the 2 states. So also the difference between, say, the A1 and the A2 transitions. And then we can fit a model to that. And we think Yeah, I guess it's really hard to know what's A1 and what's B2 because depending on the magnetic field, one should be I guess, yeah. I guess it's a little hard to always know, basically. But you can fit a model for the Hamiltonian for the SnV that you expect. And I can tell you that sort of here, the field is more aligned with the spin, and here it's not very aligned. It's maximally misaligned with the spin. And you can kind of know that from this angular dependence on the street. But everything is very dependent on the angle of the B field and whether it's and from this sweep, we can also understand the SnV Hamiltonian. So there's this sort of, to me as an experimentalist, it looks very horrible and confusing Hamiltonian that, yeah, exactly. But in this density functional theory paper from Adam Bali's group in Hungary, they sort of really understand like where the Hamiltonian comes from and all the terms. But the sort of important ones for our study are the spin orbit coupling, which sort of sets the minimum ground state splitting here. This is the thing that's 830 gigahertz, or actually it's really 822 gigahertz, I think now. I think we got it slightly wrong. But then also the strain of the diamond lattice around the qubit perturbs your color center, and it makes that ground state splitting bigger. And so for this spin orbit coupling of say 830 gigahertz, you can turn on some strain, and then the ground state splitting you get is kind of like the square root of the spin orbit coupling plus squared plus the strain squared. And it turns out your properties of your qubit for spin control and readout are very dependent on how strained or not you are. But it's important to sort of understand the level structure and to understand that you have some strain, because the next thing we want to do is spin control, and I'll show you that if we have some strain or not, that makes it work. So here I said spin control, and what I really mean by that is I want to take the lowest two energy levels, so just spin down or spin up, and I want to be able to deterministically in my experiment control it for spin down, spin up, or in some superposition of spin up and down at the same time. And I want to apply some drive that's going to rotate me around this block sphere, so-called block sphere at some rate given by omega that we can control in the experiment. And maybe before sort of launching into how we do this, I'll say before we started working on this, there was one result sort of around when I joined Yellow's group. There was one result using all optical control on the center that had a very low strain center, and it didn't work super well. Like people were still happy about it. But then we sort of understood that strain is really necessary because for the four centers in diamond, the lowest two spin states with no strain are like forbidden. It's this like forbidden transition you can't drive, and then strain breaks that degeneracy and lets you do this spin control, lets you drive a microwave field. And so last year we did this in a moderately strained center with where this ground state splitting is about 900 gigahertz, so a little bit bigger than it should be. And then there's also really nice work from Alex Hai and Mette Aditory's group, where they do this on a much higher strain center, and then also very, very recent work from Germany, which also does, they do a better job of actually characterizing the spin Hamiltonian, or this SnV Hamiltonian than we did, because they have a 3-axis vector magnet, not just, and they use multiple samples to kind of constrain the spin. So that's why I like their sort of 822 number better than our 822 number. So just want to give them a shout out. So with this strain, before we started working on this, the plot we're looking at here is an all optical control experiment where the y-axis is if you're sort of, the contrast is telling you if you're in spin up or spin down, and the x-axis is some duration of a optical control pulse. And you see these little wiggles, which shows you you're preparing the qubit sort of in a spin superposition state, like here or here or here. And you can see you have sort of 2 or 3 wiggles before it dies out, and that means you have a relatively low fidelity of your spin control because you're like, you can sort of do like 3 pulses on your spin before all of your coherence is washed out. So we want to improve this by using a direct microwave driving. And the sort of theory for this is really, as I said, if you don't have any strain, you just can't do any direct microwave control of your spin transition. So the y-axis in this simulation plot is the Rabi rate, so this rate of rotation you would expect as a function of the angle of the magnetic field you're sweeping on the x-axis for several different orientations of the microwave magnetic field drive. And so you get a very low microwave, you get essentially like a forbidden transition if you don't have any strain. But then as you start turning strain up, for some orientations of the drive, it works really well, but in general, it sort of is allowed again. And then as you turn strain more and more up, so this is about where we are in our experiment, you get a faster Rabi rate and even faster Rabi rate, where this black dashed line is essentially how well you would do with like an SnV-center, which looks sort of just like more of a free electron. And so there's this nice sort of physics that's a little confusing because it depends on the angle, the magnetic field, and it depends on the angle of strain. But there's this sort of like very general statement that more strain is good for spin control. And so we want to understand what amount of strain we have in our sample, and then we want to sort of each SnV comes out a little bit different, and then we want to select for ones that have some strain so we can spin. Any questions?
What's with the upper limit? It seems like they don't change with strain.
Yeah. So the upper limit is basically if you had like an SnV-center, how well it would. Just if you had sort of like a single electron, or something that looked like a single electron. Yeah. Did that answer your question?
Okay, I understand it.
Oh, yeah, and basically black is sort of how well you would maybe ever expect to do. Like if you did better than that, then you don't have an electron. You have something with like where like the G factor is not 2 as it is for an electron. You have something with the G factor 0. Yeah, so it would maybe not impossible, but something very unusual. So we want more strain, and then before I sort of show you how we do our spin control, the last thing I'll tell you is how we actually initialize the spin state. So I told you we want to operate at a couple Kelvin where the transitions to 3 and 4 are really frozen out. But at 2 Kelvin, 1 and 2 are really the sort of thermal energy is much greater than this like few gigahertz transition we operate at. And so everything is in this like thermal mixed state. And we can initialize or polarize the spin incoherently by driving on these optical transitions. And so this state is maybe a little confusing, but it is this characteristic decay you see when you drive on either the A1 or the B2 transition and then collect emission. And you see this exponential decay, which is telling you that at time t equals 0 here, you start in a 50-50 mixed state, and then it looks bright because your laser is kicking population up to the A state, and then it's relaxing down to the 2 state. But then when it's all in the 2 state, it looks dark when you drive it because you're driving this A1 transition, but everything's in the 2 state, and so you don't see any emission, and that's why it looks dark out at long times. And so we begin all our experiments by turning on a laser drive to polarize the spin state or put it in a down state. And that's necessary because otherwise if it is sort of 50-50, then we do our spin rotation, then it stays 50-50. We need it to be all the way down, and then so we can make it all the way up. Great. So now we're ready. So we sort of understand this general story about strain and how we need some strain to do microwave spin control to get this transition to be allowed. And we understand how we can polarize the readout or spin state with the laser. So we're finally ready to do spin control. And so the first thing we do is the so-called optically detected magnetic resonance or ODMR measurement, where we're doing, the green just kind of like scrambles everything and resets everything. Then the red laser polarizes the spin state. Then our microwave signal will control the spin state. And then our last laser will measure it. And then when we do this and we're scanning our microwave field through the transition, we see a peak here it's about 4 gigahertz set by our magnetic field. And we're very happy to see this peak because it tells us we have this spin structure that we can address. We can address with our microwave drive, not with our optical drive. And now, if you park at the center of that peak and you sweep the duration of the microwave drive, you see Rabi oscillations, which are really the sort of fundamental, like, first spin control thing you want to do in any sort of qubit. And we're happy to see them because if you remember a few slides ago, the sort of optical version of this using some other technique, things decay very fast, but now we can get many oscillations together with very high fidelity. And then this beautiful chevron pattern is what you see when you do not only sweep the duration of your microwave drive on the x-axis, but you also sweep its frequency, and it sort of makes this really beautiful pattern that we'd like to see. And we can do a pi pulse in 50 nanoseconds, so that's the time it takes to go from down to up. We can also, as we increase the amplitude of our microwave drive, the Rabi rate, so how fast these oscillations are, is proportional to the amplitude of the drive, which is expected to be. And then I will say also, we're using a massive amount of power to do this. So the spin is, we're using a wire bond, which is just sort of an aluminum wire relatively far from the sample. And that's good because it's not physically touching the sample by the qubit, so there's no like direct heating, which I think is why we can get this high fidelity. But it's bad because it's relatively far away compared to a feed line on chip. And if you have current flowing through a wire, the field decays as 1/r. And so we have to use really a lot of power. So that's maybe one disadvantage. But at the end of the day, we buy a microwave amplifier, we turn it on, and we get beautiful data. So it's a lot of power, but we also, it doesn't heat up too much. So we're happy. And so the next experiment we want to do is we want to study the qubit's phase coherence. So this is a so-called RANSI measurement. So basically the Rabi oscillations in the previous slide calibrated a pi pulse for you. So it's flipping down to up. We can do a pi over 2 pulse, so it flips halfway into some spin superposition. Then we can wait and do another pi over 2 pulse. And we see this decaying envelope as a function of how long we wait. And this measures the length of time our spins in a phase coherence, which is about 400 nanoseconds per qubit. And that's not really set by the qubit, it's set by the bath of nuclear spins in the carbon around the qubit. So we're using just regular carbon here, not isotopically purified carbon. And about 1% of all the carbon atoms have a nuclear spin associated with it. So there's this bath of spins surrounding you that you're constantly exchanging energy with at some weak rate. And that's the main thing that's limiting how fast this decays right now. We can also sweep frequency, and sort of the frequency of these wiggles are kind of how far you are from the qubit transition. And then here we're trying to be more quantitative about how we like control the qubit. So I said that, we can sort of see like 5 Rabi oscillations at once. We can have good control, but how good exactly? So now we're basically in this blue line, we're sampling on the peaks of those wiggles, and we're sweeping the number of oscillations. And we see some decay in amplitude. So I showed you essentially maybe like 5 in the plot before. Now we're sweeping it up to 50. And we see this slow decay, which we can fit to, and we can extract a pulse fidelity of about 99.5% through that. So probably if we had tuned things up a little better, maybe we could get a little flatter. But then at high numbers of pulses, it seems to drop a little bit, and we think that's some residual heating effect that we could maybe try to avoid by putting our wire closer to our chip or closer to our qubit or something.
For most of students, they might not understand how you can get the fidelity. What's the definition of
great
fidelity and what is called fidelity?
Yep. So thanks for asking. So the fidelity is really, there's the function I'm fitting to. It's very simple. It's like some amplitude times fidelity to the n, I think. Yeah, I think that's right. So like if you have a 99% fidelity, then your contrast on the second point will be 99% squared, your contrast on the third point will be 99% cubed, etc. So if you know, the fact we can sort of go all the way up to 30 is kind of like 99.5% to the 30th, I think, unless maybe with a factor of 2 or something. I can't quite do that, but it's something like that. So we're just fitting this sort of exponentially. And so that's everything I told you was the blue line. What's going on in the orange line is we're not only doing pi pulses now, we're doing a random assortment of pi or pi over 2 pulses. And the sort of lingo for this is called randomized benchmarking, and Clifford gate means like a selection of all the pi and pi over 2 pulses. So pi pulse, there's sort of, you have your block sphere describing your qubit, and you can rotate around one axis of it or the other axis of it. And it should be the same, it shouldn't matter, but you sort of do both of them just as a check. And we see when we throw in these pi over 2 pulses, we decay a lot faster. And the reason we decay a lot faster is because of the relatively short spin coherence time I showed you on the last slide. It's only 400 nanoseconds, and our pulses are kind of like 50 nanoseconds. And so if you do a pi over 2 pulse, you're in this spin superposition state, and then you dephase pretty quickly before the next pulse. Whereas with the pi pulses, you're not really staying in a spin superposition state. You're just going up or down or up or down, and the T1 or the energy relaxation time of your qubit is really long, and so you don't have to worry about it flipping from up to down. But you do have to worry about it dephasing if it's sort of difficult. So this is sort of not. I guess the overall message is like, we're doing good because we can do many pi pulses and nothing bad happens at some sort of 30 pulse level. And the fact the orange decays is some like technical thing that if you did an isotopically purified diamond, these would look this. Any questions?
So by random deposit, just randomly, it's one set.
That's right. That's exactly right. Yeah, we have like we sort of the like different rotations you can do on each data point. We like randomly choose some of them and then take the data. And then I think we're actually averaging over like 17 different random draws for each point.
I don't understand why you have to be when you choose on a X or Y gate, or then you choose randomly.
Yeah. So basically your question is like, why are the blue and the orange line a bit different? And the reason is basically the T1 or the energy relaxation time of your qubit is really long. And so when you're just in the blue line, you're just flipping from down to up and down to up. But when you're in up, you never really like relax to the down state. There's no like error mechanism there on the time scale you're doing this. But in the orange line, you're flipping, like sometimes you're flipping to the middle, and then you're flipping to the other side of the middle, and then you're flipping back. But when you're sort of in some spin superposition state in the middle of the block sphere, you're always kind of like, there's some error mechanism where you're just like rotating randomly around the equator of the block sphere, and you're dephasing, and you have this source of error from your dephasing for when you have pi over 2 pulses that you don't have for when you just have pulses. Does that help? And so the next thing we want to do, so this dephasing is kind of a problem, right? Like we want to maintain our spin superposition for a long time, really the longer the better. And so we do this so-called dynamical decoupling experiment, where now to measure our spin coherence time, we can sort of make sort of an extended coherence time by adding some control sequences within your pi over 2 pulse, then delay and another pi over 2 pulse. We can actually add some pi pulses into that delay step, and that ends up kind of, I said, you know, if you think about being on the like equator of the block sphere, and you're kind of like you're rotating at some rate randomly. If you rotate the first half of your sequence and then you flip, and then you kind of rotate back in the second half of your sequence, you can kind of, you don't know what that noise is, but you can undo it by doing this flip in the middle of your sequence. And this is essentially that experiment we're doing. And it makes the coherence time quite a bit longer. Now it's kind of, even just for one flip, you have a couple hundred nanosecond coherence, a couple hundred microsecond coherence time instead of 400 nanoseconds. So this is maybe expected for the sources of noise affecting this qubit, but it's sort of like a standard spin qubit characterization technique, and that we're happy to see and happy to see that it works.
What is it? Sorry.
Yeah, essentially, yeah. So the Han is like 1 pi pulse. This is like 2 pi pulses, and then XY4 it's like pi x pi y pi x pi y, and there's something about like if you have the x and the y pulses, it kind of corrects for gate infidelity. So if people do like XY like 1,000 or something, and they can do that with like 90% pi pulses. They don't need to calibrate their pi pulse super well, because if you do the sort of combination of the different rotations, it kind of like, in some confusing way, it kind of like undoes your gate error. But it's sort of just, yeah, it's maybe just a little technical lingo for we're just kind of like increasing the number of pulses and seeing the coherence increase. And then the final thing we'll measure about the spin qubit is temperature dependence. So we're measuring this blue line's now the T1, or the energy relaxation time, as a function of temperature. That theory line we showed at the beginning. And then the orange is the T2 time, now with 1 identical decoupling sequence, and the green is the Ramsey coherence time with no decoupling. And we can see there's this nice kind of flat regime until about 3 Kelvin, when it starts to fall off. And this sort of matches the theory, which are these dashed lines for tin. And so we're sort of happy to see this. It kind of like proves to us our qubit is robust at these temperatures the way that's expected. That we hadn't really been able to measure before, because we haven't spin control well enough. Now the last part of my talk, I'll tell you about how we measure the spin, but maybe it's a good time for questions, and I think I might be running a little out of time.
Okay, that's fine. Can continue.
Okay, sounds good.
Because they already asked many questions during the presentation.
Okay, yeah, because it's not like, yeah, the spin control stuff is or the readout stuff's nice too. So yeah, basically like point number 2 is our paper from last year. So now I've kind of gone through everything in that paper, and now I'll tell you about our paper just from earlier this week, where we talk about readout. And so everything in this part of the talk now, we know how to do the spin control, but I'll tell you how basically what's going on the y-axis and how we can make the signal in our experiment. So here we have a simplified energy diagram now, where we just have the A1 and the B2 transitions. And I'm going to define something called the cyclicity, which is kind of like the probability of decay via A1 versus A2. So the A state is kind of like also spin down, and so it likes going from spin down to spin down. It doesn't really like going from spin down to spin up. It's this like forbidden transition that's actually weakly allowed a little bit. And exactly how allowed it is has really big implications for readout. And again, we're gonna talk about how we sweep the angle of our magnetic field in our experiment. And this parameter zeta is really important, because that's sort of the experimental knob to control how the angle it's doing. And then, so this here, the green line is the sorry, I forgot to say the pulse sequence, but it's the time since we turned on a laser drive driving on just the A1 transition. And we're looking at the time tagged emission we get from the qubit as a function of how long we turned on the laser drive. And we can see at some angles of the magnetic field, this decay is really quick, like tens of nanoseconds. And then at some angles where the magnet is more aligned with the spin, it's really long, like kind of 10 microseconds. And so this is really important, because in the green case, the cyclicity is high, and it's emitting many more photons before it polarizes into this other state. In the left case here, cyclicity is low and is polarizing really quickly, which sort of limits the number of photons you can get out of your experiment. And so for improving your readout, you really want to understand this trade-off, and you want to understand to make sure you operate sort of where the cyclicity is high so that you can get the most photons out. But there's a disadvantage there too, in that it takes longer to do stuff. And so we can measure the cyclicity now as a function of the angle of the magnetic field. So we're sweeping again in this sort of 2D circle set by the two axes of our magnet. I really wish we had that. It would be so much easier, because then we can kind of calibrate everything better. But from doing this cyclicity measurement, we can sort of see that cyclicity is highest at some angles, and from comparing to a model, we think that corresponds to being sort of about 10 degrees misaligned when we're doing the best. So we have our chip on some rotation stage, so we try to align it so this number is maximum. But it's a little hard to do that because each time you rotate it, you have to kind of realign. So we just kind of do the best we can, and we think we're about 10 degrees off. And when we're about 10 degrees off, cyclicity is about 2,000. And so we didn't really understand this trade-off very well for the last part of this talk, and we were operating around cyclicity of 100. But now we're going to kind of understand this trade-off better and operate around 2,000, and that's going to let us do a lot better. And then we also went down like a really long rabbit hole of just improving all the optics in our experiment, making better filters, making sure we're better aligned, fine-tuning the position to understand we were on a mesa, understand exactly the brightest spot to look in our chip. So we did all this, but the sort of physics thing we did was really try to align with them. Is there a question? Yep. So now we'll tell you how we characterize the readout. So we prepare our qubit. We're going to do sort of two experiments. There's like a pink waveform here where we prepare the qubit and spin up, and then a blue waveform where we prepare it and spin down. And so and then we do that. So this is like a laser pulse. This laser pulse on a different transition, and then we're going to measure the qubit also by driving again on a laser transition. And then we're going to repeat this many, many times, and we're going to look at the time tag counts we get out of this measurement. And we see sort of two different distributions depending on if we prepare the qubit spin up or spin down. So in the pink, if we prepare the qubit spin up and then we drive on the same transition, it looks very dark because the spin has polar. Like really, I think the conceptual thing it's confusing to me about color centers, but confusing in general, is that your spin polarization and your spin readout steps are the same. They're both driving on one of these optical transitions. And this is like, if you have like a superconducting qubit or something, that's like totally ludicrous. Like it doesn't make any sense. But for these atomic systems, you really are just like, these pulses are just driving on the transition. You drive on the same transition twice, it looks dark. You drive on different transitions, it looks bright. And the fact you have these two different distributions lets you sort of discriminate your spin state with high fidelity. So if you get 1 foot, like if you do this, you have this distribution, and then you do another shot of the experiment, and you get 1 foot on that shot. It's a little confusing to know where you are, but if you get 5 photons for that shot, you know you're in this blue distribution. You know which one you prepared it in without having to look at your waveform. So this is called single shot readout. It means you can sort of measure the qubit state with high fidelity. And then to kind of check this, we're going to do this readout, and then we're going to show it's compatible with spin control. We're going to do a high pulse for one of the waveforms and not for the other, and then do a second readout. And that's going to sort of invert the histogram we get. And now the colors are different. So now we get sort of more photons out in the second readout step. And the fact they're inverted as they should be sort of shows you this high pulse is doing what it is expected to do, and it shows this single shot readout is compatible with spin control, which is not really for granted in these type of color center qubits. And then sort of from some looking at the separation of distributions, you can by the sort of standard metric people use, which is kind of like the error probability of being on one side of this threshold line, we get sort of an 87% fidelity and about 50%. So, I wish it was 99%. I wish we had 50 photons in our bright distribution instead of 4. But at a sort of rudimentary level, this is showing that is working. And then we can also, because we have these two measurements, we can look at correlations between the two different measurements. Basically, this is sort of another way of selecting the data. You could keep, if you're trying to measure your spin qubit or something, you can, instead of just doing one measurement, you can do this sequence with two measurements in it at the end of your cycle. And then sort of post-select only the cases where the two measurements were different. And that would, it's like cheating a little bit because it lets you claim a higher fidelity, but you're claiming that higher fidelity by kind of like post-selecting away some cycles of the experiments. You're not gaining information about your qubit state any quicker. You're just kind of like post-selecting. But it's kind of fun to show. People do it in this field. So that's kind of how the readout results work. And then we also study the sort of power dependence of this readout. So here, right, I told you the readout steps are all driving one of these optical transitions. And we're, how hard are we driving, right? How does readout depend on how hard we're driving the qubit? And so we sweep the power in our optical drive, and we keep track of the number of photons out in the bright or the dark distributions. And it has this sort of characteristic thing where the pink, the one that should look dark, gets noisier at high powers, and that's because some of our noise comes from the optical drive leaking into our collection path. And sort of higher powers, it gets noisier for this technical reason, basically because we don't have good enough filtering. But the difference between these, what we really kind of want to optimize, saturates at some power, which is expected for these color center qubits. It's set by kind of the physics of that energy level structure and alignment of all those transitions. And basically by sort of looking at the value it saturates to, the number of photons you expect to get out your experiment is basically the cyclicity is this sort of probability we were looking at a few slides ago, the cyclicity times the efficiency. So it's saying, cyclicity is like 2000. So every time I turn the laser drive on, it's going up and down and up and down and up and down about 2000 times before it goes to this dark state I'm not driving. But I'm actually, before I was getting 4, now this was slightly worse day in labs, we're only getting 2 photons out. And sort of the difference between these, or the ratio is about 0.1%. And so that's saying of relaxation events of our qubit, we're only recording that as a collected event 0.1% of the time. And which is obviously, we'd like this to be much higher, but it's sort of, last year it was a lot worse. So we're making steady improvement. And then, here's a plot where you have power on your x-axis and efficiency on your y-axis. And we're kind of about here right now in the readout I've been showing you, where we have this 10 to the minus 3 efficiency and kind of, okay fidelity. It's like in the single shot regime, but it's not, it could be better. I think that we're mainly limited by the fact we're not really in this optimal photonic structure. There's sort of, there's loss in the detector, there's loss in between our qubit and detector. There's some intrinsic loss in the defect itself, just because remember I'm collecting the phonon sideband, so all the 0 phonon line light we're throwing away right now. We don't need to do that in principle. But the main source of loss is the scattering of the light just elsewhere, not into our detector, not into our collection path. And so if you sort of did like reasonable improvements in all aspects of the experiment, you could operate maybe much higher efficiency. That's good for making any sort of quantum network. It's nice in lab because it lets you take your data a lot better, lets you study longer spin coherence times. The fact we stopped at 16 dynamical decoupling pulses in the spin control wasn't because we couldn't do more, it's because our readout was bad and it was taking a long time to average. So if you have higher fidelity, you don't need to do that, you can study longer things. And so we're excited to sort of improve this in the future. And then in the final few minutes, I'll just tell you about this sort of nice story about weak measurement and dephasing in quantum mechanics that we can. We sort of here we study weak measurement by changing the power in order to better understand the efficiency of our device and show it compares to our model. But I also want to tell you about how we use this weak measurement to study kind of also characterize how the lasers interact with the qubit. But it's kind of a nice, fun demonstration of how quantum mechanics and measurement really work. So now we're doing this dynamical decoupling sequence to prepare the qubit in a spin superposition state. And then, so we have, this is basically a laser drive to polarize the spin. These are our microwave control pulses. This is our projected measurement, so a sort of high power readout of the qubit. But then this is some drive of variable duration and variable power that we put in the middle of our sequence. And so at the beginning of the sequence, we prepare the spin superposition state. But then when we do this controlled weak measurement, that also dephases the qubit. And then we get a reduced spin superposition after this weak measurement as a function of how hard we were trying this. And this is a very precise way of studying how strongly the laser is interacting with the qubit, because you have this good way of measuring the qubit spin coherence with your projected measurement at the end of the sequence. And so you can really understand like how much a small amount of power is dephasing the qubit, and maybe avoid any sort of other effects that show up only at times.
So here you measure this weak pattern.
That's right. We're I say we have a weak measurement, and I'm going to show you exactly how weak it is, or how not weak it is.
So the last step is just selection.
Yeah, the last step here is a strong projected measurement, I would say. Yeah, like every measurement I've showed you, almost every measurement up until this point has been a strong measurement where I'm just sort of blasting the laser at some, power about as high as I can make it in the experiment. And now I'm gonna like turn that power way down in this measurement in the middle. Yep. And what we see is the following. So on the left here, on the x-axis, I'm sweeping the time of this weak measurement. On the y-axis, I'm measuring signal I get at this measurement at the end. And on the different colors, I'm using different powers of this weak measurement. So for the highest power, the contrast I get reduces quickly. This y-axis is essentially like how much spin superposition I still have left after I do this weak measurement. And so as I turn up the power, this phase coherence I still have left reduces very quickly. But at low powers, like I can keep my weak measurement drive on for a long time and not really perturb the qubit very much. And so it's sort of showing you that more power perturbs the qubit, which is expected. But then by fitting exponential decays to these, we can really precisely study how strong the laser is interacting with the qubit, by looking at the sort of decay rate of these curves. If that kind of qualitatively makes sense. And then we sort of do that comparison here on the right, where now on the x-axis is the power for these different measurements. These are just 4 different selections at different powers. And then on the y-axis, we're plotting the decoherence rate, which we get from these fits. And we can see that as we turn up the power in our laser drive, we're decohering the qubit faster and faster. And basically, there's sort of a nice story. I can refer you to our paper, but basically the slope of this curve, kind of comparing that slope to the slope of this curve, how fast it goes up, is like another way to characterize the efficiency of your detection. And which is nice because it sort of relies just on this shorter measurement at lower power, not in the high power. Because in the high power limit, like there's something that happen, like if you blink off and go to the charge state, you might have more scattering of your sort of like from noise in your system. So with that, I'll conclude the talk. I'll say at the beginning of the talk, I told you about the SnV qubit motivated for quantum networks, and I told you about spin control. And then in the last part of the talk, I told you about spin readout. And then in the future, we're interested in incorporating these devices into nanophotonic structures to get better efficiency. We're trying to control not just the spin of the tin-vacancy center, but some like surrounding pure spins at the time, in which all of these, there's really nice blueprints for this from like SnV-centers or other color center qubits. Like these aren't like new ideas. We're just sort of interested in understanding how well they work for this tin-vacancy qubit. And then maybe one day there will be some tin-based quantum networks. I think this is sort of a step along. So thank you very much.
Thank you very much. So let's be first. The impressive work and where you guys stop. I guess there will be some other questions from audience, especially from students. Please ask more questions. Yes. Okay.
Please go back a few slides to the KAPAN.
This
So this is question is the star.
Yeah, that's right. So yeah, sorry, maybe I forgot to say that the color axis is kind of readout and fidelity. So you want to be up in the top with the readout best. And I think we're kind of like here right now.
Okay, so in the understanding, what is the most recent development or state of the art in this graph?
Oh, for us, the most recent thing is here. I think this is kind of where I want to be. Or really just anywhere higher is where I want to be. And I will say also the only other single shot readout of tin and diamond is this other paper. And they were kind of like here. So they're a little, they don't characterize the efficiency, but it's lower because they're just enough volts.
How about other vacancy?
Other vacancies are much higher, yeah. So with like I think the silicon vacancy center and diamond work is a lot more mature than tin. And what they do with these silicon vacancy centers at the group at Harvard is they integrate the vacancy into a photonic cavity around the transition. And then they don't quite do the readout the same way as us. They do the readout by probing transmission through the cavity and seeing the cavity frequency like shift a little bit depending on if the spin is up or down. And that lets them get much higher fidelity in much shorter times. And it's really because they have this like photonic structure that's interactive. So basically compared to other types of qubits, this is like really, yeah. Okay, I mean in my PhD work, right, we did superconducting qubits and the efficiency there was like 7%. You know, so everything is like, yeah, this is like a first step, not actually. Yeah.
Yes, another question, please. We still have a lot of time. Pak Agung.
So you're posting around one signal entity
That's right.
in one location.
Yep.
And then you have like many different entity feedback center in different locations. So how you break this concept and then scale it out or just doing quantum mechanics?
Yeah. No, that's a really good question. So I think there's like, it's kind of crazy, right? Because there's like, I have millions of qubits on my chip, but for the last like year, I've only been measuring one of them because I think there's like some reasons for that. They all come out kind of different. So we're not like doing anything to our diamond chip to get the strain we need to do spin control. We're just kind of like, depending on how you prepare your chip, you might have some different distribution of strain or not. But it's in the sort of like times we've tried to search for new emitters, it is a little bit hard for us to get stable strained emitters, for reasons we don't quite understand yet. So I think that sort of, that plus like the system is sort of not super optimized for scanning right now because we have this nano positioner scanner, but the field of the range you can scan is like kind of 100 by 100 microns. It's not like the whole chip. And so that makes it a little bit harder. But I think for scaling things up, you can imagine having like a chip where somebody fabs like, thousands of devices on it. And then you have some really optimized like scanning setup so you can sort of characterize the like strain and the optical properties very quickly in a way that like is totally possible just in my setup right now we don't have. And then you can be like, oh, okay, like of these 1,000, like the one in like row 10, column 20 is like the best. So just like focus on that one. And then that chip is like done or something, So I think there's a path to scaling there by post-selecting devices, but it's obviously not ideal, that is a challenge.
Yeah, so would you mind to show the spectrum that you showed optical transition and phonon sideband?
Yep. Yep.
Well, I'm not sure whether it's correct or not, but is the phonon sideband is something like a noise or something? Or
Yeah, that's a really good question. So it's sort of like it is supposed to be there, and for different color centers, each color center has sort of a different way it emits into the photon sideband that's set by the sort of properties of the color center and the properties of the host material it's in. And you know, I think if you are trying to make quantum networks that relies on sort of some like indistinguishable photon emitted from your qubit, which has to come from this like well-defined optical transition, then I would call it noise. But for my experiment, where I'm doing readout by only collecting it, I would call it signal. So it's something that's supposed to be there that you can sort of use for readout. You know, if you found a qubit that only didn't have a photon sideband at all, that only emitted into its zero phonon line, that would be great. I think the field would sort of prefer that. Yeah, but.
so now that you mentioned readouts, does it happen to be related to spin readout as well?
Yes, that's right. Yeah, I would say it's like we're sort of using emission or lack of emission into the phonon sideband to make a determination about if our spin is up or down. So we're measuring the spin state based on looking at emission. Yeah, that's right.
Well, perhaps we can discuss later.
Absolutely. Yeah.
Thanks. Thank you. So other questions? Maybe I just have one basic question regarding the number of nodes.
Yeah.
So why so far only 3 nodes as the state of the art?
Yeah. So I think that's a good question. I think it's because there's a lot of technical challenges. So, I mean, you saw this whole talk, right? It's like we do the spin control and we do the readout. But this is kind of like, you know, there's not like a million groups in the world all doing these experiments. There's like, we have to get the cryostat, we have to get the laser right, and we have to do all this control electronics. Like, I think I have a fun photo. And so, you know, I mean, it's a big field. There's plenty of people doing that. But as soon as you get 2 nodes, that means you have to have 2 devices that both work. And right, I was saying there's a lot of kind of like post-selecting around for a device we really like. So that kind of slows things down. Yeah, this is kind of what our lab, this is about like all the equipment you need just for one experiment. But there's a lot of kind of like post-selecting to get a good device. And then that kind of slows you down if you have to do that twice and get those devices to kind of have similar properties. And then you have to worry a lot about the timing between the different control electronics, right? So like your pi pulse in your one cryostat has to arrive at exactly the same time as the pi pulse in the other. And I think that's okay if it's in like one lab next to each other, but it's actually kind of hard to do if your lab is like 100 meters away or something. You know, you might worry about some of this, you know, so there's a lot of like little things that kind of about them. And it's, you know, the NV's been around for 20 years, but it's not like, you know, it's I think we'll improve the number of nodes, but it's and then, you know, there's a lot of inefficiencies in the experiment, right, which should have slowed things down.
Can we just get an estimate how many nodes will we expect within 10 years?
And I think there will be on average maybe 1 node per year. Like on very like optimistic estimate. I don't know. It depends kind of, yeah, I don't know. But I think it's both a sort of hard problem and it's a little bit unclear like why the world needs it now. You know, there's some like papers about like longer baseline telescopes and stuff. Yeah. But even maybe in 10 years from now, I think we'll have like 6 nodes or something. 6 nodes. So yeah, that's the final answer. You can send me an email 10 years from now. Okay, tell me about.
You did weak calibration.
Sorry,
Calibration.
it will be measurement.
We measured it? Yeah, the last couple slides, yeah. That's right.
Do you have in mind some application of it?
No, that's a good question. I think it's I think the best application is that I know of right now, and maybe there's better ones, is really to characterize this efficiency number better. So we really, like, when you're kind of benchmarking how well your device works, you really care about how much of the light you're getting out. Like, say I make some qubit in a waveguide or something, and I want to know if I'm getting a good waveguide and it's collecting light well. I want to really measure this efficiency well. But then if I just turn up the power, there's sort of noise that increases, and there's also these like blinking or charging processes that increase. So I want to measure this efficiency in some like standardized low power way. And I think the weak measurement really provides a method for doing that. That's sort of new for these color centers. We got the idea from superconducting qubits. There's like a very similar method, like superconducting qubit literature. But I think for color centers, it's maybe not the only way to characterize the efficiency, but it's like a good low power one. And to me, that's used as like a guy who's like trying to like figure out if my devices work or not. That's useful. It's sort of all over. I mean, it's just kind of fun to see that it dictates it. I don't know. Like I like seeing that it's sort of, it's not a surprise, but like on a basic level, it does. It's sort of one of the many checks that quantum mechanics like works as a shit, which I also.
Okay, thank you very much. Maybe one more last question. You put the time on screen. If you have satisfied? Yeah, if you are still not satisfied, then we can discuss later at the seminar. So let's give applause once again for our accepting our invitation, and hopefully you will enjoy your stay. How many days?
A week and a half.
A week and a half. We will visit Sumatra Island. Hopefully everything is okay. Okay, thank you very much. So let's close this seminar, and we will get together again here around 5 p.m. because we will have dinner. Yes. Okay, thank you. That's all.